So this is 2.5 exponential function context and data modeling. Exponential function context and data modeling. It says sometimes data from an exponential function does not display a proportional growth pattern. So I couldn't go in and divide one number by the next number and get something that's the same every time. But that doesn't mean that it's not exponential. It could still be exponential. This might be due to a vertical translation of the function. So it could be that all of our data points are shifted a little bit off, and there is still an exponential growth pattern, but you can't see it because of the output values. Okay? So if we can subtract or add a constant from the output values to realize how they shifted, and we can go back to the original, then it's possible that we could find out what the growth rate actually is. It's really hard to do that, okay? I think it just comes from some intuition about numbers in general, okay? But we're going to practice. We're going to try it. Let's everybody look at example 1, the first table there. It says selected values from several exponential functions are given in the tables. For each, find the constant value that could be added or subtracted to the output to reveal a proportional growth pattern. And then we're going to write the equation. Once we figure out what's actually happening, then we can write the equation that goes with it. Okay. So our output values here are 7, 13, 25, 49, and 97. They got shifted up one. From what? From 6. 6 became 7. Okay? So if 6 got shifted up 1 to 7, then something got shifted up 1 to 13. What would that number have been? Oh. So he thinks it's 6. He thinks that everything went up 1. Let's verify by checking. If I started at 6, my next number should be 12. Is that shifted up 1 to 13? And then what would my next number be if we continue with the same growth rate? 24. And then? 48. So what are we doing here? We're doubling. After 48, we became, should be 96, but on the table it's 97, right? So what happened? We had, my initial value was 6, right? That's what happens when x is 0. So it was 6 times, what's my growth rate? What's it doing every time? Doubling. So 2 to the x power. But what I see on the table is plus 1, right? So if I took my f of x functions and shifted them down 1, I would get 6 times 2 to the x. Can you see that? If I took my output values and shifted them down 1, then I have the equation 6 times 2 to the x. So the question is, what's the equation of the stuff in this table? Well, f of x must equal, if I add that 1 to both sides, then this f of x function must equal 6 times 2 to the x plus 1.
This is cool.
Huh?
That plus 1 doesn't go up there with
No, not with the x. No, because this is a vertical shift. And so this is an outsider that tells the truth. We have a visitor. The question is, how do we know it's 6? It's because that's what I have when x is 0. So we are always in the form f of x equals a times b to the x power. And a is always what's left if x is 0. Because if I raise b to the 0 power, that part goes off. Anything to the 0 power is 1. So you're left with a. That's your initial value. It's the y-intercept. It's every time what you have when x is 0. Oh, not 6 in the function. How did we know?
Couldn't you just do like the 13?
You just really, sorry, the hardest thing to explain, you have to look at it and kind of guess. You have to see, like, what are these numbers doing? They're almost doubling.
Couldn't you just do like the minus thing that we did? Like how, like could be. You can't do that?
No, because that's going to give you rate of change.
Ah,
That's not going to work on an exponential function.
okay.
So I looked at it and I thought, they're almost doubling. Twice of 13 would be 26. 2 times 26 would, like, it wants to be doubling, but it's not quite double. You know what I mean? But it could be doubling if I had started with 6. And what you're adding or subtracting to every number is going to be the same every time. So they are all shifted up 1. Can you see that?
Okay.
Let's try letter B. Try letter B.
This one's hard.
This one is hard,
I
for sure.
thought it was going to be.
I know they're going up by 3.
Okay?
Our dilation is 3.
Feels like it's a dilation of 3. That's a great idea. He said it feels like they're getting 3 times as big every time.
Well, they are. They're ready to change.
Somewhat.
Okay?
Like 2.
It's tripling. I will go there. What's tripling though?
The
The 1.
year change.
Okay? It's tripling. The growth rate is tripled. Well, what's 3 times 10 would be... So what? If you shifted them all... Is that right? Okay, Grace says if I shifted them all up 2.
No, because 24 plus 2 is 34.
Okay, but if I started at 4,
And then 26.
what's 3 times 4?
12.
12.
What is it?
What's 3 times 12? 36. 3 times 36? 3 times 36?
108.
108?
Yeah.
3 times 108? 324?
So it's not that.
It is.
What?
He said, so it's not that. It is that. Look, if all of these numbers were shifted up 2, this would be our function, right? With a growth rate of 3.
How did...
Oh!
No, because I just did like 2 to 10 is 8. 10 to 34 is 24. 34
You're
is
finding rate of
Yeah, that's
change.
what I was
That's what
asking.
Ruth was saying too. It's not rate of change. This is not linear.
Because that's how I got the first one.
It's not linear. So the growth rate we knew was 3. These things are getting about 3 times as big.
So it's being triple.
And so then you have to go in and kind of figure out, well, what's the wiggle room on that?
Triple plus 2.
So why did we just start at 4?
Why did we start at 4? Because that's the magic number that when I triple it, gives me the constant rate of change for everything else.
Hey, I get it.
Dude, I'm so lost.
This is why we're doing the homework in class tomorrow. Okay, so
Okay.
the growth rate here is 3. What I can tell here is if I took my g of x minus 2, right? If I took my g of x, the g of x function that I see right here on paper, and I added 2 to it, what I would end up getting is 4 times, so the 4 comes from, that's the initial value,
4 times
3 to the x,
Okay. Yep.
okay? But what I actually have, g of x, is a vertical shift down from that by 2.
Okay.
So what does g of x actually equal? G of x, the table, is equal to 4 times 3 to the x power minus 2.
Okay.
Oh, okay.
So my function wanted to be 4 times 3 to the x, but it got shifted down 2, and that's where the values in the table are coming from.
So this next one,
Okay, so he's ready for the next one. Is everybody else ready for the next one?
Yeah.
you would look at it, it's about a 1/2.
Okay, looks like they might be halving. Yeah, now we're on to something. Looks like they might be about halving. Okay,
So I think you start.
so if where could I start?
You can start from the bottom, can't you?
So they would be doubling going up,
Yeah, but it's still like going down.
shifted down 1, can you tell?
Yeah, it's like
Because what would I actually have started at? 64,
30.
right? If I started at 64, then what's half of 64?
Wait, so if it's going
32, half of 32 is,
to the
half of 16 is 8. Half of 8 is, you just kind of have to start somewhere and see if it holds. I can.
Do it with 2 as well, and then instead of like.
Well, you got to be really careful because you're finding rate of change, and you have to go from 0 forward. If you start at the bottom, you might think it's doubling.
Okay.
It's not doubling.
Okay.
It's halving. Does that make sense?
Yeah.
Okay. So Ruth's question was, couldn't I start at the bottom and see what's happening? Yes, but you got to know that you're doing it backwards. Because if you start at the bottom and you say my numbers are doubling every time, then all of a sudden you think your growth rate is 2. And your growth rate's actually half.
Okay.
So you really need to start at the top of the table and go down from there. So on that one, the eyeballing said, it looks like they're getting about half as big. So now you got to pinpoint numbers right around there that you could half it and tell. And it's a shift off of half. What's the shift off of half? -1. Okay, so what do I have here? I know my initial value. Okay, so after you do your exponential regression, you should see it tells you A equals 30.089 and B equals 1.25. Y'all see those? You can use that information to write the equation at the bottom of the example down here. It says use the given data. So what do you know? You know A equals 30.089 and B, the growth rate, is 1.25. Your equation is supposed to be, they put right here, f of t equals A times B to the t. So f of t equals 30.089 times 1.25 to the t power. There's your equation.
Whoa.
Actually, yes. That is what I got when I did it by hand. Not gonna lie. I mean, it was nasty. And I was like, and then I saw the calculator thingies and I was like,
This is why you always read the whole question.
this is why you read the whole question. Yeah, so your answer here, your function, when you plug in the values that you got for A and B into A times B to the x.
I don't know how she did mine. She did it.
It was
Wait, so A is
30.089.
and G of K is A.
How would you even do it by hand?
No, I go.
So I plugged into this one, G of n equals G of k times r to the n minus k. And I split my 2 points. I called this one n and G of n. And I called this one k and G of k.
And work from that.
And so I plugged into that. I went backwards. I solved for r. And then I picked one of my points and I wrote the function.
Oh, that's yucky.
It was yucky.
And you did it all in that little space.
Lesson learned. Use your calculator.
Space that's right above where it shows that.
Yeah.
It says you use the given data to write 2 equations. So do we have to do another one or just that one?
I think your other equation could have been if you had just plugged in, right? So you could have said, I would have swapped and I would have put this one to be the k stuff. So instead of using n and g of n and k of g of k, I would have put the bigger number as n. So n and g of n and k and g of k. So when you plug in, you could have had 2602 equals 47 times r to the 20 minus 2. Right? And this is an equation. So there, done. You see? This is how I did. And I solved for it backwards and upside down and on my head. All right, let's go on to example 3. Because this is just more practice of the same thing. It says selected values of the exponential function g are shown in the table, where g of x equals a times b to the x. Use the given data to write an equation that can be used to solve for the values a and b in the expression. And even on the, so write two equations, okay? Well, g of x equals a times b to the x. I've got two separate x values here. So I could say that g of 3 equals a times b to the third. Or I could say g of 8 equals a times b to the 8th. There. Two equations that can be used. Both of those are true. Do you see what I'm saying there? Now, I didn't find the values of a and b. That's part 2. But part A says, write the equation, write two different ones that could be used. And both of these work.
So you just take your x value,
Yeah.
make the function of that.
Sure.
And put that as your x.
Plug it in for x. What's wrong with that? There's two good equations. Then question B says find the values of a and b. So this is where you go in your calculator. You're going to go to your list and spreadsheet. You've got two values for x. So on your table in your calculator, for x, you're going to have 3 and 8. For y, 21.54 and 3.62. By now, I realized I could just use my calculator. And so there was no more handiwork here. No, we don't have to solve it right now because they didn't tell us evaluate for. They could, though. What'd you get for A?
62.
And for B? 0.69 or 0.7? So we write g of x equal to 62.80 times 0.7 to the x power. And did you store this equation in F1? So the reason we do that is because now you can go to your home screen. Everybody do control page and do calculator. Now you can calculate what is g of 6. What is g of 6? So on your calculator, you're able, when you put it in F1, you can put var, and you can go to F1 of 6, and you ought to be able to plug in a 6 and output a number. 110? Is that right? I don't think I would get 110. It'd be between 21 and 36, right? Or 21 and 3. 7.38? 39? Okay, so we're going to pause the recording for just a second. Everybody look around and find your neighbor and make sure they understand how to get that F1 value pulled up on the home screen. Okay, this is a skill we have to have. We'll try to cover example 4. We're not going to get all the way through. Not even close. Not even close. All right, so example 4, it says the natural number e is often used as the base in exponential functions. Remember that we could have a logarithm of base 10 or a base anything, but if the log happens to have a base e, we call it the natural log, okay? I just really feel like we're going to hold off on this part until tomorrow. Yeah, we'll start this whole second piece tomorrow.